general relativity, step by step. We've got this beautiful expression for the stress-energy tensor for a perfect fluid in its rest frame. And it's this nice diagonal matrix here with rho 0 and p's on the leading diagonal and zeros off place. I'm going to focus on what it means to talk about in its rest frame, and I'm going to express the stress-energy tensor in a different way in order to make it clear how it transforms. Oops. Just a minute, let's pinch in there. So what does it mean to be in its rest frame? Well, we've got a little control volume. I'll pinch in a bit more. Little control volume, here it is. And it's full of some stuff there. It might be water or air. And what I've got here, there's me. And I'm looking at this control volume here, and I'm wondering what its stress-energy tensor is. And of course I've got an answer, P0, 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 with zeros off the diagonal. The problem is that we've got a preferred reference frame here. There is one reference frame that is different from all the others, and that's the reference frame in which that fluid is at rest. So there's me. I say the fluid is at rest with respect to me, and that's why I calculate this particular form for the stress-energy tensor. And of course, as soon as you've got another reference frame, such as Baz, here's Baz in his spaceship, he's sitting there, and his spaceship is cruising along here at some very high velocity. What does Baz see? Well, he sees something different from me. Just a minute. Go back to black. Baz will see, at least he will see the energy density going as rho 0 gamma squared, as we've talked about before. So what I need to do is to figure out how to express the stress-energy tensor in such a way that it makes it clear what Baz perceives the stress-energy tensor to be. And in order to do that, I've got to express the stress-energy tensor T in terms of physically meaningful quantities. So what have I got at my disposal? I've got rho 0 and P0. They're the rest densities and pressure. I suppose there's just one density, isn't there? Just rest density. There it is. And that's the density and pressure as measured by someone at rest with respect to the fluid. What else have I got? I've got U. I've got I'll give it an index there. I've got a 4 velocity. And I've got one other trick up my sleeve. I've got G alpha beta, which is my fundamental tensor. My metric tensor. Which in this case is -1, 1, 1, 1. That's the metric I'm using in this course. At least I think I'm trying to use it. I'm trying to be consistent about it, but not always entirely consistent. And what, of course, we want is this beautiful diagonal system here. Now, we know we've got a U alpha, U beta in the expression for T alpha beta equals that because of this gamma squared term here. And so that will make, we need to multiply U alpha by U beta to make that gamma squared term correct. We can't just multiply it by a rho 0 because that wouldn't give us the correct transformation. It's not entirely obvious how to do this. What you need to do is rho 0 plus P0 times, oh, I don't need another set of brackets, I'll get rid of that. U, this is T alpha beta equals that. U alpha, U beta, but that's not quite right either because that gives us a sum there. We need to, do we need to add or subtract it? We need to add. I had to think there because there's different conventions for use for the metric tensor. We need to add P0 times G alpha beta. Well, that's the answer you get in the books. I mean, you sort of led to that inexorably by the mathematics and the physics, but I just wanted to verify that it's correct. And that equals, I'm going to talk about it in a few minutes, but what that equals is the stress-energy tensor, stress-energy tensor, the fluid moving with 4 velocity u, with components u alpha and u beta in your particular reference frame. So I better verify that it works. Of course, so what if U equals, what happens if it's still? What happens if the fluid is at rest? What happens? Well, there, your fall velocity is just 1, 0, 0, 0. It's just a single vector of unit magnitude pointing in the time direction. So we can just evaluate this this expression here, and what we get is that T alpha beta equals rho 0 plus P 0, and then zeros everywhere else, because we're taking a cross product effectively of U with itself, 0, 0, 0, 0, 0, 0, 0, 0, and that is the first component here, plus P0, which is this second component here, times the metric tensor, which is that. Is that right? Yes, that's right. So very conveniently, the pressure here cancels out with the pressure there, and we are left with rho 0, we are left with rho 0, 0, 0, 0, 0, P 0, yes, P0 from here, 0, 0, 0, 0, P 0, 0, 0, 0, 0, P 0, as expected. But of course, I can put any velocity I like in here. So let's just say that you're moving. Let's just say my U is, I'll pinch in a little bit. I might say that U is gamma U 0, 0. Because you're moving, or the fluid at least, fluid is moving with 3 velocity U 0, 0. So of course when we work out the 4 velocity we have that gamma term and the gamma U there. So what does that do to my stress energy tensor? T alpha beta equals, it's always as good, always as well to write it out, rho 0 plus P 0, U alpha U beta plus P, that's a 0, 0 G alpha beta. This is all in flat space. Flat space. My writing. Let me do that again. Flat space. Okay, so what does that look like? Well, U alpha U beta drawn in matrix terms is going to be gamma squared, gamma, what is U again? U is gamma U 0, 0, gamma squared U, gamma squared U, gamma squared U squared, and then zeros everywhere else. I need another row and another column of zeros, plus P 0 times the fundamental tensor, which is that. So what have I got here? That's going to be equal to, oh, that's P0 plus rho 0 times. Yeah. To get the stress energy tensor, I need to say that T alpha beta equals this lot here. So when I work throughout here, I get P0 plus rho 0 gamma, looks like the power gamma squared minus P0 for that term there. Here's going to be a P0 plus rho 0 gamma squared U. This one's going to be the same. This term here is going to be a gamma, it's going to be the same, but gamma, we've got P0 plus rho 0 gamma squared U squared plus P0, and then 1, 2, 3, 4, a whole bunch of other zeros, and we've got P0 there and P0 there. So there's the stress. I'll just pinch out a little bit. That's T alpha beta for Baz moving with respect to the fluid. And we can see that we've got off-diagonal terms that correspond to momentum transport, or for momentum transport or for momentum density. So it's quite a complicated expression. The diagonal form's bad enough, but this accounting for, it's not quite a Lorentz transformation, but it is what it is. It's a second order tensor expressed in a different reference frame. Stress energy tensor. I'm going to stop right there.